Welcome to a lesson with Dr. Pal. In this video, we will look at some practice problems where we practice verifying that a statement of a limit that's given satisfies the definition of a limit that's in terms of epsilons and deltas. So just verifying that the epsilon delta definition that we have for a limit is actually working in the specific case. Of course it works, but and of course this limit, understanding that we know that this limit will be 1. If you just plug in 3, you will get 1. But the point is, let's practice, thinking about these logical precision ideas of epsilons and deltas and how that's actually correlating and working really nicely and well in this particular instance. So this is problem number 1. I invite you to pause the video and try it out on your own and think about it. And then, and when you're ready, let's go ahead and see the solution. All right, on your mark, get set, go. Okay, now here's the solution on this one. Okay, so what we're going to do, let's first remind ourselves what the statement is that we're going to be verifying. That is, given epsilon greater than 0, so we're thinking we have a straight line slope of -1. So it's coming down like so, slope of -1, straight line, and it looks like our x values are heading toward 3. Maybe this point on the graph, let's let that be x equals 3, and it looks like we're heading toward a y value of 1. And about this y value of 1, what we're going to be doing is we're going to be selecting a distance that goes up and down epsilon. So we can kind of picture it like this. Okay, so that's what that means when I say given epsilon greater than 0. Now, in the statement itself, we say there exists. Now, in order to verify the statement, we're actually going to find what it is we're saying exists. There exists delta greater than 0, a little distance greater than 0. So we're going to actually, to verify this, basically it just amounts to determining what the delta would be in this particular situation. There exists some delta, just like epsilon's a distance, delta is going to be distance. There exists that such that what? Such that if our x values are such that if you subtract where they're heading, which is 3, so this is like the distance from x to 3. So the distance from x to 3, if it's non-zero, so basically we're saying if x is not 3, yet the distance between x and 3 is less than that guy, delta, what would happen? Then the distance from the actual function, so if you want, you just call this equal to f of x, distance between the actual function and 1 will be less than epsilon. Okay, so basically the function is going to be in here. Is there a delta value, a distance away from this point here and here, that would ensure that the function would be between these two lines? Because that's basically what this means. The distance from the y value of the function to 1 is going to be less than epsilon up and down. Yeah, I mean, if we just go to the point of intersection here of the line, of this line so the line y equals, this top line right here is y equals 1 plus epsilon. This bottom one is y equals 1 minus epsilon. If we're looking at the intersections of these with the function itself, which is right here, I'll just write in f of x right here. So if we just go to there and notice, because it's very symmetric, because it's a slope of -1, it's going to be the same distance to get to this point of entry exit as it is to get to this one. Why don't we just call that distance delta? That's an acceptable delta if we were to use that going that way and that way. All right. So in the picture, we actually just saw it. We just saw that there is a delta in this particular situation. We verified this is holding. Why? Because this is given epsilon, meaning any epsilon. Any epsilon we choose, any distance, no matter how close we get it to this point, how small the epsilon value is, there's always going to be a delta. Now, in particular, a computational way of specifying that there actually does exist a delta is to say what delta is. Let's say what delta in this particular situation. The situation depends on what? It depends on epsilon. All right, so meaning delta should depend on epsilon. Let's see, this slope right here is a slope of -1. So, and we know we're going over delta, and yet this right here is epsilon. Well, that tells you automatically this is a 1-to-1 ratio, which means delta must be the exact same as epsilon. So really what we can do then in our statement, we're just going to change there exists part. So instead it says let delta be equal to epsilon, and then we can come over here and say then if this is true, then that's true. And our verification pretty much is the picture and the idea that the ratio of epsilon to delta is a 1-to-1 ratio. And that's pretty much it. Okay, so this idea and the picture tell us that this is acceptable, and this is the delta that exists, so that this all works. We just verified the statement. Now, we didn't verify it using some kind of inequality type thing algebraically. We did it a little bit with pictures, but with ideas and intuition, honestly, this is pretty equivalent to what we were just doing algebraically. We just kind of did it graphically. If someone wanted to do it with inequalities, it pretty much is equivalent to the picture and the ratio idea. So why may as well just do it this way. All right, if we're going to do it like that. Okay, so in this particular case, at least for a problem as simple as this, for intuition's sake. All right, so that was practice problem number 1, and that would be okay. Now let's take a look at another practice problem when we're taking limits. Okay, and we will reserve that next practice problem for the next video. Thanks for watching.